Here is the problem. We are handed a transfer function g of s equals s plus 3 divided by 3s to the fourth plus 3ks cubed plus 4s squared plus ks plus 1/3. Inside the denominator sits a free parameter k. Our job, find every value of k for which this transfer function is stable. Stability of an isolated transfer function means one thing only. Every pole, every root of the denominator polynomial must sit strictly in the open left half plane. The numerator does not matter for stability. The 0 at -3 plays no role here. So the question reduces to one polynomial, 3s to the fourth plus 3ks cubed plus 4s squared plus ks plus 1/3. For which k does every root of this fourth-order polynomial sit in the open left half plane? Solving a fourth-order polynomial by hand for arbitrary k is brutal. The roots are messy functions of k. We need a smarter root. That root is Routh-Hurwitz. The strategy. Routh-Hurwitz gives stability without ever computing a single root. It works in two stages. Stage 1. The necessary condition. For every root to sit in the open left half plane, every coefficient of the polynomial must be present and share the same sign. If any coefficient is 0, or if the signs disagree, the system is already unstable. Done. We can stop. Stage 2. The Routh table. Build a table from the polynomial coefficients. Compute its first column. Stability is equivalent to the statement that every entry in the first column shares the same sign. No sign changes top to bottom. When the polynomial has a parameter like k inside, the entries become expressions in k. Each entry that depends on k becomes an inequality. The system of inequalities taken together gives the k range for stability. We will run both stages, necessary condition first, then the full Routh table, and combine the constraints at the end. Stage 1. The necessary condition. List the coefficients of the denominator in order: 3, 3k, 4, k, 1/3. Two of them carry the parameter, 3k and k. The other three are fixed positive numbers. For the necessary condition to hold, every coefficient must be strictly positive, same sign, no zeros. 3 is positive, always. 4 is positive, always. 1/3 is positive, always. 3k is positive when k is positive. K is positive when k is positive. Combine. The necessary condition fires once on a single inequality, k greater than 0. If k is 0 or negative, the system is already unstable, no further work needed. K greater than 0 is necessary. Whether it is also sufficient, that is what the Routh table will decide. Stage 2. The Routh table. Lay out the first two rows directly from the coefficients. The s to the fourth row collects every other coefficient starting from the leading term, 3, 4, 1/3. The s cubed row collects the remaining coefficients, 3k, k, and a trailing 0 to fill the row. These two rows are written. The remaining three rows must be computed. The recipe is the same for every cell. Take a 2x2 block, the leading column from the previous two rows on the left and the column above and to the right of the cell on the right. Take the determinant of that block. Divide by the leading element of the row immediately above. Move on to the next column. The structure is mechanical. Compute s squared row, 2 cells. Compute s to the 1 row, 1 cell. Compute s to the 0 row, 1 cell. 5 cells total. Then read the first column, the s squared row. 2 cells to compute, both built from the first two rows. First cell, call it B1. Take the 2x2 block. Top row, 3 and 4. Bottom row, 3k and k. Cross multiply. 3k times 4 is 12k. 3 times k is 3k. Subtract. 12k minus 3k is 9k. Divide by the leading element of the row above, 3k. 9k divided by 3k is 3. B1 equals 3. The k cancels. The cell is a fixed positive number with no dependence on k. Second cell, call it B2. Top row 3 and 1/3. Bottom row 3k and 0. Cross multiply. 3k times 1/3 is k. 3 times 0 is 0. Subtract. K minus 0 is k. Divide by 3k. K divided by 3k is 1/3. B2 equals 1/3. Again the k cancels, another fixed positive number. The s squared row is now 3, 1/3, 0. Both non-trivial cells are positive constants. The k dependence has bubbled away. The s to the 1 row. One cell, call it C1. Take the 2 by 2 block from the previous 2 rows. Top row 3k and k. Bottom row 3 and 1/3. Cross multiply. 3 times k is 3k. 3k times 1/3 is k. Subtract. 3k minus k is 2k. Divide by the leading element of the row above, 3. C1 equals 2k divided by 3, or equivalently, 2k over 3. Here the k survives. The cell depends on k. The s to the 0 row. One cell, call it D1. Take the block. Top row 3 and 1/3. Bottom row 2k over 3 and 0. Cross multiply. 2k over 3 times 1/3 is 2k over 9. 3 times 0 is 0. Subtract. 2k over 9 minus 0 is 2k over 9. Divide by the leading element of the row above, 2k over 3. 2k over 9 divided by 2k over 3. The 2k cancels. What remains is 1 over 9 divided by 1 over 3, which equals 3 over 9, which equals 1/3. D1 equals 1/3. The k cancels again. The bottom of the table is a fixed positive constant. The first column of the Routh table is now complete. From top to bottom, 3, 3k, 3, 2k over 3, 1/3. Stability requires every entry to share the same sign, and since the leading entry is positive, every entry must be strictly positive. Walk down the column. 3 is positive, no constraint on k. 3k is positive when k is positive, 1 inequality. 3 is positive, no constraint on k. 2k over 3 is positive when k is positive, same inequality repeated. 1/3 is positive, no constraint on k. 2 of the 5 entries depend on k and both demand the same thing, k greater than 0. Combine with the necessary condition from stage 1, also k greater than 0. The two stages agree. Final answer. The transfer function g of s is stable for every k greater than 0 and unstable for every k less than or equal to 0. A clean parametric stability boundary at k equals 0. Above the boundary, all 4 poles sit in the open left half plane. At or below the boundary, at least one pole crosses into the right half plane and the system blows up. Verification. We have a clean answer, k greater than 0 for stability. Let us spot check by plugging in numbers and looking at the actual step response. Top left panel, k equals 2, comfortably inside the stable region. The step response oscillates briefly, then settles to a finite value. Bounded, stable, matches the theory. Top right panel, k equals 0.1. Still positive but close to the boundary. The response rings longer. The small k starves the damping, but it still settles, stable, just barely. The boundary is reached gracefully from above. Bottom left panel, k equals 0. Exactly on the boundary. The necessary condition fails. One coefficient is now 0. The response drifts and oscillates without bound, marginally unstable as predicted. Bottom right panel, k equals minus 0.5, below the boundary. The denominator now has a coefficient of the wrong sign and the response explodes. The curve runs off the chart, strongly unstable as predicted. 4 data points, 4 matches. Routh-Hurwitz delivered the right answer without ever computing a single pole. Summary. The problem. G of s equals s plus 3 over 3s to the fourth plus 3ks cubed plus 4s squared plus ks plus 1/3, for which k is the transfer function stable. The method. Routh-Hurwitz. Necessary condition first, then the full Routh table. The Routh first column, 3, 3k, 3, 2k over 3, 1/3. The constraints. Only 2 entries depend on k. Both demand k greater than 0. The answer. G of s is stable if and only if k is greater than 0. The big idea. When a transfer function carries a free parameter inside its denominator, the Routh table converts the stability question into a system of inequalities in that parameter. Solve the inequalities, get the stable range. No root finding required. The same method scales. It works for any parameter, any number of coefficients, any order of polynomial. The parametric stability boundary is the most useful tool a control engineer carries into design.